Now we can start, I think. Okay, so hello everyone. I'm Edi Baskoro. Good afternoon to all of you, and welcome again to the 2023 Combinatorics Today series. It's our great pleasure to see you again in this wonderful occasion. First of all, I would like to thank the Faculty of Mathematics and Natural Sciences for the continuing support and the encouragement in conducting this series. And I'm very happy that through this series, we could invite prominent combinatorists from all over the world. Today, we will have a very special speaker from Czech Republic. Please have a big welcome to Professor Daniel Kráľ from Masaryk University. And I would like to mention that this program is brought by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, with collaboration with the Center of Research Collaboration on Graph Theory on Combinatorics Indonesia. So now I let Dr. Inovia to chair this session.
Okay, thank you, Pak Edi. Okay, so before we start, I would like to apologize because we have some technical difficulties with our connection. So I would like to introduce our speaker today. Our speaker is Professor Daniel Kráľ from Masaryk University in Brno and also the University of Warwick. He graduated with master degree in computer science and also doctorate degree in computer science from Charles University in Prague. And also he has a second doctorate degree from the Czech Academy of Science. He started his academic employment in TU Berlin as a postdoctoral fellow. And then he also worked as researcher in Charles University in Georgia Tech, in University of West Bohemia and Pilsen. And he became a professor in University of Warwick. And after that, professor also in the Faculty of Informatics in Masaryk University in Brno, starting from 2018. He's already published more than 150 papers in journals and also 28 in conference proceeding, and with more than 1,000 citations. He also he was the editor-in-chief for SciEM Journal of Discrete Mathematics and also managing editor for two very top journals, Advanced in Combinatorics and also GCTB. He was awarded with the European Prize in Combinatorics in 2011, the Philip Prelifer-Holm Prize in Mathematics and Statistics, and also he is a fellow of the American Mathematical Society. And today, Dan will give a talk in our Combinatorics Today series, and he will talk about the quasi-random combinatorial structures. So please, Dan, the screen is yours.
Yeah, so thank you for the introduction. And it would be nice if somebody can signal that I can be heard. Just some nice gesture will do from anybody who can hear me. Or just confirmation that I can be heard.
Yeah, we can hear you clearly.
Perfect.
Everything
Thank you.
is clear.
So the topic of today's talk is quasi-randomness in combinatorics, which has been a theme in my research for a couple of years now, and it's very closely linked to the theory of combinatorial limits, which has been occupying my research interest for even longer time. So the plan for today's talk is the following. First, I would like to review some classical results on graph quasi-randomness, which goes back to the 80s. Then I would like to present a very brief introduction to the theory of combinatorial limits and use it also as an excuse to talk about some very recent work concerning so-called stem graphons, which do corresponds to stochastic block model in statistics and network science. And then I would like to talk about results analogous to the classical results that I will mention at the beginning, and which concern tournaments, permutations, and Latin squares. So this is the plan for the next 60 minutes. I try to be maybe a little bit briefer, but at the same time, I would like to encourage you to keep asking questions, and I will try to also monitor the chat. So if you have problem with your mic or you prefer asking a question in the chat, then I am going to be following the chat too. So let me start with this with the historical overview. As I mentioned, the results of quasi-randomness can, as we know it today, can be traced back to the 80s, but the concept or the notions or various notions or various attempts to capture what it could mean when the structure looks like a random one, of course, even predict this nowadays classical notion of quasi-random graphs. So when we want to say that a graph is quasi-random, we want to say it somehow resembles the Erdős-Rényi random graph GNP. And it's very hard to say about one specific graph that it resembles the Erdős-Rényi random graph GNP. Because if in principle, so maybe I should recall that the Erdős-Rényi random graph GNP is a graph that has n vertices, and we put an edge between any two of them with probability p independently of the other edges. So in principle, we make it a complete graph, even if the probability, when let's fix p to 1/2, even if the probability is exponentially small in n squared, we make it also the empty graph. We make it a complete bipartite graph, but it's very unlikely that we will get one of these graphs. So most likely we will get some graph that does not have one of these very specific structures. And the question is, like others, none of the specific graphs is more likely than the other, but what is kind of a typical structure? What are the typical properties of such a graph? And since it's very hard to talk about a single graph, being quasi-random is actually a property of a sequence of graphs, because now we can be saying that this sequence could have been generated with high probability as a sequence of Erdős-Rényi random graph. So when I will be talking about quasi-random graph, I will not be thinking of one specific graph, but I will be rather thinking of a sequence of graphs, and I will be thinking or asking myself whether this sequence could have been generated by the Erdős-Rényi random process. So the notion, which these days is considered to be the notion of quasi-random graphs, goes back to the 80s, to the work of Redl, Thomason, and Chung, Graham, and Wilson. And let me now present the notion. So the notion, I will be referring later to it as a notion based on substructure densities. And for that, I need like two definitions. So the first definition is the definition of an induced density of a graph, and this is the probability that if I pick randomly 3 vertices in my graph, I will see the graph H. So it's a property of a graph H. So I will see my graph H as an induced copy. So for example, if H is a cherry, then these 3 vertices form an induced copy of the cherry in the graph. However, if I would have chosen maybe these 3 vertices, then they of course contain a copy of a cherry, but not as an induced graph. So I wouldn't count this triple in when considering the induced density of the graph. And another notion, and we will see in a second, where do not give different concepts of quasi-randomness, is the notion of homomorphic density, which is the probability that if I take my graph H, so let's say my graph H is still a cherry, and I take a random mapping to the host graph, so I randomly map the vertices to the vertices of the host graph, what I'm going to see will be a homomorphism, meaning edges are mapped to edges, and I don't have any restrictions on what edges. So in particular, another possibility would be to map this triple, for example, to these three vertices in this way. So I will get a possibly non-induced copy of the cherry. And I said that the notion of quasi-randomness that I will be looking at in this talk is based on subgraph densities. So I will say that the sequence is quasi-random if the induced density of every graph H in the sequence, so this is for every graph H, goes to its expected density in the R-any random graph. So for example, if I'm talking about the R-any random graph Gn 1/2, so if I'm setting P to be 1/2, then I would expect the induced density of the triangle to be in the limit. So I have a sequence of graphs with let's say with the number of vertices going to infinity, and I would expect, or I require that the induced density of the triangles goes to 1/8. The induced density of the cherry would go to 3/8, and so on. And equivalently, which is not hard to see because this is just one can apply the principle of inclusion and exclusion, because if one knows that the induced densities of all graphs on k vertices, one can compute the homomorphic densities of all graphs on k vertices and vice versa. The definition is equivalent actually to requiring that the homomorphic density of every graph in the sequence tends to the expected homomorphic density of that graph in the R-any random graph. So this is the definition of quasi-randomness. One may of course say this looks a little bit random. Like, why don't we pick a different definition? And in the paper Chung, Graham, and Wilson, we actually observe that this definition is equivalent to many other definitions or other properties where the sequence of R-any random graphs have a probability 1. And if I have a sequence of graphs and has one of these properties, it has any of the other properties, and I listed some of them on this slide. So we have already seen the first two. The first one is the property of having the right limit or the correct limit of the induced subgraph densities. The second property is having the correct limit of the homomorphic densities. And somewhat surprisingly, so let me remind you that what we require is that we require this to hold for all graph H. However, somehow surprisingly, the limit of the homomorphic density of every graph in the sequence is its expected density in the R-any random graph, if and only if actually the limit of two of these graphs is the right one. So what we need is, so we instead of checking all graphs, it's enough to look at the homomorphic density of two graphs, namely the H and the C4. So it's enough to look at the homomorphic density of the H and the homomorphic density of C4. And if I have a sequence of graphs where the homomorphic density of the H is P, which is its expected density in the sequence of the R-any random graph, and the homomorphic density of C4 is P to the 4, then the homomorphic density of any other graph is expected density in the R-any random graph. So for example, the homomorphic density of a triangle will be P cubed. The homomorphic density of the cherry will be P squared, and so on. And so I will maybe come later. Let me present the other three properties first. And when another, so I prepared here some pictures which I was hoping might be illustrative. So the first definition says when we're looking at the homomorphic densities of all graphs or the induced density. Instead of all of them, it's actually enough to consider just two specific subgraphs, an H and a cycle of length 4. And it was later to show that actually the cycle of length 4 can be replaced by any even cycle, and the forcing conjecture of Skokan and Thoma actually says that the cycle of length 4 can be replaced by any bipartite graph that contains at least one cycle. And another property that a truly random graph would have with probability 1 is some equidistribution of the edges. So if I have a random graph, I don't expect that I would have a very large copy or very large subset that would have too many edges or too few edges. So what one would expect is that if I have a graph with capital N vertices, if I have a graph with capital N vertices, when I do expect that if I take any subset of small n vertices, let's say, which is linear in the capital N, then the number of edges that I will see on that subset, so this is, let's say, a subset of n vertices, is roughly Pn squared over 2. So this is the number of edges I would see in a truly random graph with some small deviations. So let's say I put plus minus little over 1 square. And it's not only that I would see the equidistribution on subsets, I will also see the equidistribution of edges between subsets. So if I take any two subsets A and B, such that both A and B, again, I wish to be linear in the number of vertices, then I will again expect that the number of edges between them is roughly what it would be in the truly random graph. And the last property is the spectral property. So if I get a sequence of arbitrarily random graphs, and this sequence actually, the limit of its spectrum is somewhat simple. But like the graphs are almost regular, so one will get an eigenvalue which is roughly p times n, and all the remaining eigenvalues will be sublinear in the number of vertices. And the result of Chun, Graham, and Wilson, building on the earlier ways that I mentioned on the previous slide, says that if I have a sequence of graphs satisfying one of these properties, then it satisfies any of the remaining 5. And I would like to particularly draw your attention to the equivalence, to this equivalence, which says that instead of testing possibly, or instead of testing countably many graphs and their densities, it's enough to look at 2 subgraphs. And this will be actually a theme going throughout my talk, where I will be looking at characterization by finitely many subgraph densities. So what I wish to be doing in this talk is looking at different substructures. I mentioned tournaments, permutations, and Latin squares, and looking like if I take the substructure density of quasi-randomness, so I will take the density based on having the right counts in the limit of all substructures that I can see, either in induced or non-induced settings. When if there's a finite set of substructures, like in this case K2 and C4, that actually would capture the quasi-randomness. So it would be enough for the sequence to be quasi-random just to be looking at the densities of these 2 specific subgraphs. So I think this might be a good time for questions. I just kind of provided a very brief overview of the very classical results of quasi-randomness, and my next plan is to look at these results through the views of the theory of combinatorial limits. I will provide a very brief introduction to this theory, and as I mentioned, I use it as an excuse to mention some of the recent results that I have with 2 of my colleagues, Andrzej Grzesik from Krakow and Oleg Pikurko from Masaryk. So I pause here for a couple of seconds in case there are any questions. I don't see any in the talk. If you wish to ask a question, feel free to unmute, and I will be very happy to answer it. It does not seem to be the case, which might be worrying, or maybe everything was clear, but just let me proceed. But really, if I mean, I don't mind like skipping one of the bullet points that I have prepared for the one of the topics that I have prepared for today's talk, and I would be very happy to answer the questions even before the discussion which is planned after the talk. So as I promised, I want to be looking at the problems of quasi-randomness through the lenses of the theory of combinatorial limits. And first, I want to generalize the notion of a quasi-random sequence of graphs. So we said that the sequence is quasi-random if the homomorphic density of every graph converges to its expected density in the average random graph. So this is this line. And the more general definition is a definition of a convergent sequence, where I require that the homomorphic density of every graph converges, but I do not prescribe the value. So in particular, if I have a sequence of graphs that is quasi-random, that sequence is convergent, because that was a part of the definition, which is exactly written here. But if I have a convergent sequence, it doesn't need to be quasi-random. So for example, a quick example of a sequence which is convergent and is not quasi-random is a sequence of a complete bipartite graph with the numbers of vertices split in the ratio 1 to 2, which I have drawn here. And it's not hard to verify that the homomorphic density is of, if I take this sequence like with n going to infinity, that the homomorphic density of any fixed graph H converges. And the theory of combinatorial limits actually builds a way how to represent limits of such sequences in an analytic way, but these analytic representations are actually linked to the structural properties of the or asymptotic structural properties of the graphs in the sequence. So let me maybe first do the kindergarten view of graph limits, and then I will just mention that actually this kindergarten view works in the sense that we do not lose like the key asymptotic properties. So the kindergarten view would be that if I have a, let's say, complete bipartite graph like the one drawn here, then I will look at this adjacency matrix. So its adjacency matrix has kind of a block structure where I have a part corresponding to the two independent sets in my graph. Between these two sets, I have ones, and inside these two sets, I have zeros representing non-edges. And if I let n to go to infinity, then this discrete structure, in some sense, becomes a continuous object. And the object is a function from 0, 1 to squared, where 0, 1 corresponds to the segment. And actually to 0, 1, even in this case, it's actually not an interval, but it's just two values, where I have value u1, which I denote, which is depicted by black, corresponding to edges, and white areas, which corresponds to non-edges. And I should say that now what I'm doing is that the beginning of the coordinate system for me is in the top left corner to have the analogy with the matrices. And it's actually the case that in statistics, people actually put the beginning of the coordinate system to the bottom left corner, which is the usual drawing. But since this talk is more focused on combinatorics, let me keep using this notation in the analogy of the adjacency matrices. And the funny thing is that even if this may look like kind of a naive approach how to represent an adjacency matrix of a large graph, Borgs, Chayes, Lovas, Westerkombi, and their collaborators established that actually this representation, if one properly defines the homomorphic densities of graphs for integration, when these representations link to the structural properties of the graphs in the sequence. And it's highly non-trivial. Like one needs to use like regularity decompositions to establish the existence, martingale convergence, and so on. So it's not trivial to do, but it's possible to do. So I will not be like presenting the theory. I will not even aim to sketch, but I just want to hint that even if this approach may look like natural, there's actually some deep mathematics behind it. And I prepared here a couple of more examples of graphons. So this limit object, and that's the first time, or maybe the first time on this slide I'm using this word on this slide is called graphon. So this continuous version of the adjacency matrix, that's a graphon. And I prepared here, in addition to the graphon corresponding to the complete bipartite graph with parts in the ratio 1:2, I prepared here 3 more examples of graphons. So the first one, this one corresponds to complete bipartite graphs with parts of equal sizes. This one is an example where actually the density is not an integer, it's a value, let's say 1/2. So this one corresponds to actually having the edges distributed uniformly throughout the graph. So this is actually the limit of the sequence of the, if let's say P is 1/2, of the sequence of the linear random graphs G and P. So this will be the graphon representing the sequence, the quasi-random sequence of graphs, a quasi-random sequence of graphs. And the last graphon is a union of cliques, where I have a clique on half vertices, and I have a clique on quarter vertices, 1/8 of vertices, and so on. So what we're now asking, what are the conditions when the graphon is the constant graphon, is this one, which is the graphon corresponding to the sequence of to a quasi-random sequence of graphs. So now I can recast this classical result of the classical result which I have mentioned in the beginning, which, if you recall, the quasi-randomness of a sequence of graphs was captured by the densities of 2 specific graphs, an H and C4, and when the sequence is quasi-random, if and only if its limit graphon is constant, which is equivalent to the graphon having the density of K2, the H at P, and the density of C4, P to the 4. And actually, let me just mention that if I fix the H density, when the quasi-random graphon is the one minimizing the density of C4, so this simple observation might be important for some of the questions or topics that I will look later during the talk. So let me now mention some of my recent work with Oleg and Andrzej, which I have mentioned earlier. And this work is motivated by so-called K-step graphons, which, as I have mentioned, correspond to the stochastic block models in statistics. So this is a generalization of random graphs, or if you wish, quasi-random graphs. So in the linear random graph model, we put edges between all vertices with the same probability. In the K-step graphon corresponds to a different model of a random graph. And in this model, we first split vertices into capital K parts. So in the examples below, we have K is 1 in the first case. In the second case, we have K is 2, and in the remaining 2 cases, we have K is 4. And for each of these paths and for each pair of these paths, we may have in principle a different density or different probability of putting edges between. So of course, if we have just one part, we recover the original model of the linear random graphs, and but in principle we may have more parts, and then we get a more general model of random graphs. We may have some structure, but the amount of structure is heavily controlled by this parameter K. And Lovász and George observed that the K-step graphons are characterized by vertex subgraphs where the number of vertices is bounded by a function of K. So recall that if K is 1, then we know that it's enough to look at the density of these two graphs. So it's enough to look at the density of 4 vertex graphs. And what they showed is that there is a universal constant, where it's a function of K, but it's enough to look at the densities of graphs if at most this function of K vertices. When Lovász later improved this bound to a polynomial of K, and then what we did with Andrzej and Oleg, we actually obtained bound which we improved the degree of the polynomial and actually also the constant, and we showed that this K to the 8th can be replaced with K squared and with rather reasonable constant. So our result is written holds only if K is at least 2. For K is 1, we would get 3, which is not correct, but it holds from K2 to on. And what we proved is that, for example, if K is 2, whatever will be the densities appearing in the blocks. So if we choose like this density to be P, this density to be Q, and these two densities to be R arbitrarily, when if the densities of all graphs with at most 14 vertices are the same as in the step graphon with 2 parts, then it's actually that step graph. So I will not be like giving details of the proof, but I want to mention even a more specialized case of this result. And that's an extension that was considered originally by Spencer. But if we assume that the vertices in different parts have different degrees, then he observed that actually the original bound, which at the time of when he was looking at this problem was not even polynomial, it can actually be linear. And with Andrzej and Oleg, we also improved the leading term in this bound. We actually showed that instead of 8K minus 4, it's enough to take 2K plus 1. Unless K is 1, then we actually need one extra vertex. And I should mention that in the general case, unlike the previous results where the argument was more algebraic, our argument is actually constructive, and therefore we're hoping that it may be more relevant to the problems in network science and statistics. So I think this might be again a good time to ask questions if there are any, because now I want to leave the realm of graphs and look at a little bit more general problems, namely the problems concerning quasi-random tournaments, quasi-random permutations, and Latin squares. So again, I will pause for a couple of questions. Sorry, a couple of seconds. I do apologize. And if there are any questions, please either unmute yourself or ask them in the chat. And also, if I manage to lose you a little bit with the step graphons and maybe graphons in general, the beginning and the results concerning tournaments, even if I will again be mentioning combinatorial limits, like I will be primarily formulating them in the language, in the combinatorial language without limits. So you may reconnect to the talk and follow it again. There's still no questions. So I will move to tournaments. I said I will be combinatorial. I promise the results will be combinatorial, but I think it's best to start with saying what is the limit object, what is the limit theory. So let me first recall what is a tournament. A tournament is an orientation of a complete graph. So I'm going to assign to orient each edge of a complete graph. I may get an acyclic orientation or an orientation with directed cycles. The two tournaments that I've drawn here, the one on 5 and 6 vertices, They both are transitive tournaments. That means they do not have cycles. So it's possible to order the vertices, but all edges goes from a smaller vertex to a larger vertex. And similarly to graphs, it's possible to develop the regularity theory for tournaments, which would yield an analytic representation of large tournaments. And this analytic representation will naturally leads us to a combinatorial object, which in the analogy to graphons, I will be calling tournamentons. And this object represents how many edges are directed from one kind of group of vertices to another. So if I have no structure, similarly to the previous case, I'm going to get a tournament which is constant. If I have all edges oriented in the transitive way, so let's say I have the limit of these tournaments drawn in the left, when all edges will kind of go from smaller to the larger vertices, and this would be captured by all edges actually being just in the top upper triangle. Because so if I look, so I will just put one if there's an edge, if the value of the tournament kind of represents the density of edges going kind of from kind of a small neighborhood of A to a small neighborhood of B, or small neighborhood of X to a small neighborhood of Y, if you prefer. So I will be just seeing edges going from smaller to larger vertices. And of course, I can get some more complicated structures like the one drawn here. So again, I have functions, but at this time I don't not symmetric, as in the case of graphons, because we're kind of in this motivation that I was giving, we were corresponding to the limit of adjacent symmetrices. But I have instead of this condition, which says that if I have two groups of vertices, when the number of edges going from one group to the other plus the number of edges going from the other group to the first is actually all edges. And when the question comes, which tournaments have this property of being quasi-random forcing? Like in the case of graphs, we have seen that if I have the right density of edges and C4s, when the sequence is quasi-random. So now I'm asking, so it doesn't make quite sense to ask about the right density of edges because it's always 1/2. I have an orientation of a complete graph, but it makes sense to ask what are the tournaments such that if in the limit I have the right density of these tournaments, when the sequence is quasi-random, which corresponds to the tournament of being 1/2. And it's not hard to see. And this was well known in combinatorics, and when proved using analytic methods by Corigliano, Parente, and Rasborov, and that all transitive tournaments have this property. And of course, the question is, are the transitive tournaments the only one? And the answer is no. So there's actually an additional 5-vertex tournament, which is quasi-random forcing, and that's the one that I have drawn on the right. So it's let me circle it. It's this one. So it has kind of an interesting structure because it's formed by 2 cyclic triangles, namely these ones, with all edges which share a vertex, and then all remaining edges are when oriented from one of these triangles to the other. And also what is somewhat funny, if you recall, I was mentioning that quasi-random graphs are density minimizers of C4. So quasi-random tournaments are density minimizers of transitive tournaments, but they're actually density maximizer of this 5-vertex tournament. So it's somewhat interesting that we have a characterization where we have graphs which in the quasi-random setting minimize the density, or tournaments that minimize the density, but we have this exceptional 5-vertex tournament that is actually the density maximizer. So then, of course, the natural question is, are there any other? And Bucic, Long, Shapira, and Sudakov, they actually were looking at not only at this notion of quasi-random tournaments, but also at some of its generalizations. And they in particular observed that there is no additional 7-vertex tournament. So the question that was left open is, for tournaments up to 6 vertices, and in quite a lot of cases, the answer is obviously we're not quasi-random forcing, but in some cases actually not so obvious, and it requires some work. And this is what we did with Robert Hancock, Adam Kabela, who were my students, Tajza Martin, who were my postdocs, Tajza Martins and Honza Volec, who were my students. Fiona Skerman was also my postdoc, and with Roberto Parente, who we visited, or some of us visited in Brazil. And we showed that actually, somewhat surprisingly, in addition to transitive tournament, this 5-vertex tournament, which is really the only additional quasi-random forcing tournament, which for me is actually a big surprise, because usually when one has an infinite family and one gets another graph that is somewhat exceptional to it, it usually leads to a constructions of finitely many, which was already excluded by Gucic, Long, Shapira, and Sudakov. But perhaps there can still be some additional small sporadic examples, but actually not the case. This is the only one. And I should mention that the only proof of its quasi-random forcing that I am aware is actually based on flag algebra. So there's no really kind of structural, maybe I would even dare to say combinatorial proof of its quasi-random forciness. So let me now maybe slightly deviate from the topic of quasi-randomness, but I will come back to it. And I want to talk about one extremal question for tournaments. So we're still staying in the world of tournaments, so meaning orientations of complete graphs. But now I want to look at the following extremal graph theory question. So if you give me a tournament, I want to be looking at the number of cycles of length k. So I want to be looking at the cyclically oriented. So I have orientation. So the objects that interest me are orientations, are cyclic orientations of an unoriented cycle. So for example, this is an oriented cycle of length 5. And I want to be asking, what is the maximum possible density of such cycles in a tournament? So the minimum is easy, because I can take the transitive tournament, so minimum is 0. And the answer is the maximum. Clearly, I have a lower bound coming from the random setting. So in the random setting, of course, it depends how we look at it. Let's say we look at the homomorphic density. So in the homomorphic density, I'm going to get 1 over 2k. If I would be consider different flips of orientations, I will need to multiply by 2. And the question is how much better I can do than in the random setting. And there are some results. And the case of oriented 3 cycles, that's actually a classical result from the 40s, when one can prove that actually the random tournament, or if we wish, the quasi-random tournament, is the maximizer for the density of cycles of length 3. However, the situation becomes much more interesting, and I actually prepared the example. I will show it for cycles of length 4. But for cycles of length 5, we're back in business. The quasi-random tournaments are again the maximizers. So let me show you the construction for the let me show you the construction for the cycle of length 4, which is better than the quasi-random one. So what I'm going to do, I'm going to take n vertices and I put them in the cycle. So these are my vertices, and I put them in the cycle. And if I take any particular vertex, I will look at the forward arc, this one, and orient all edges from this vertex to the vertices lying on the forward arc. So all these edges which are here are oriented from this vertex, and the edges which are, let me change the color, and all the edges which are on the backward arc are actually oriented towards the vertex. And now I will rotate the picture. So I have a cyclic orientation, I have a cyclic order on the vertices, And every vertex, if I have two vertices, I look where, like I take the shorter arc between them and orient the edge in the cyclic way on that arc. So basically, so this is one vertex. Now I have the second vertex, third vertex, and again the same rule. So these are the backward arcs, and these are the forward arcs. So I just take the vertices on a circle and orient edges between them based on their position on the circle. And this simple construction actually beats the random construction for cycles of length 4, and it actually beats the random construction for cycles of any length divisible by 4. And the number that one gets is actually the number which is shown here. And actually, it's I mean, not so hard, but like not so easy to show when this infinite sum, which involves pi's, when k is 4, when this sum actually gives 1/6, when sums to 4/3 together with multiplied by 2 plus 1. And so what we know is that we can beat the number of cycles in the quasi-random setting if where length is divisible by 4, and if the length is not divisible by 4, when we press cannot beat it, and this was conjectured to be actually the case by Bartley and Day. So what they showed is that what they conjectured is that if k is not divisible by 4, then the random construction is the best possible, and if k is divisible by 4, then one can beat the random construction. This was the example, but they conjectured that this example is actually the best possible. And what we did with Andrzej Křešík, László Miklós Lovász, that's not the Lovász I mentioned earlier, it's his son, and Honza Volec, we actually proved this conjecture for k not divisible by 4, and we have shown that for the case k is divisible by 4, when the conjecture, at least the leading term, is the right one. So if you look at the expression that I have, you can see the leading term from the infinite sum, and we also verify the conjecture for k is right. So now this actually brings us back to the quasi-randomness, and what we see here is that another object, in addition to transitive tournaments, if we in the non-induced setting, that forces quasi-randomness is that cyclic orientation of a cycle as long as the length of a cycle is not divisible by 4, because that's exactly what this with a little bit of work, what this implication is saying. So what so when it, of course, the question comes, what is special about cyclic orientations? Are there any other orientations that are quasi-random forcing? So this is the reformulation of what we shown with Andrzej, Laci, and Honza. And when we were looking at this problem with two students, like one of Andrzej and one of mine, with Daniel and Bartek Kilak, and using spectral arguments, we managed to characterize which orientations of cycles up to length 10 are quasi-random forcing and which are not. We have some general results, so actually our results do apply to cycles of any length, but they give a full characterization only up to the length 10. And we were hoping, but unfortunately this hope did not work, that we may, if we see the particular results for cycles of length up to, let's say, 10 or 12, then we will kind of see some general pattern. But as you may see, like the first line are orientations of a cycle of length 8, which are quasi-random forcing. The second line are those that are not quasi-random forcing. The directions of edges are color-coded, but somehow it was not. We tried like different ideas, like looking like at the parity of edges forward, backward, like homomorphisms to some specific graphs, but neither of them seems to work. However, what is somewhat surprising to us was that in all cases, like what we actually need to do, we need to work with the spectra. One may think of the spectra of tournaments, or one may think of the spectrum of the associated operators, but all the arguments are actually spectra. So again, this might be good time for questions, and I should also maybe agree with Eddie or with somebody else. I don't know with whom would be the best to agree when I should stop, because I started a little bit later, so I may still have like 5 to 10 minutes, right?
Yes, you do.
Yeah, well, thank you.
Okay.
So what I will do is, I think I will skip the Latin squares, but I will go very quickly through permutations. Because permutation, first of all, the limit object is somewhat different, and there are actually some nice open problems that I would like to mention. I also have a summary slide with open problems, so I will go quickly through them. But let me go now quickly through permutations. So the first question is, like for graphs and tournaments, it was obvious what is a subgraph and what is a subtournament. So we may ask, what is the subpermutation? And I should say at this point that I'm a combinatorist, I'm not an algebraist. So for me, a permutation is not, I don't look at its algebraic structure. I'm not thinking of like group of permutations, like composition. For me, this is just a linear order on numbers from 1 to n. So in other words, I have 2 orders on endpoints. One is telling me the order from left to right, and the other order is telling me the numbers, the order from 1 to n. And with this notion in mind, if I wish to define a subpermutation, let's say I have this permutation of order 6, I look at the 6 elements that I have chosen. The smallest one becomes 1, the second smallest becomes 2, and the largest becomes 3. And so this is the subpermutation induced by the 3 underlying let elements is 2, 1, 3. And if I look at the other example where I have 3 blue underlying elements, the smallest become 1, which is the last of them. The second smallest is 2, and the remaining one is 3. So with this notion in mind, one can define when a sequence of permutation is quasi-random if the density of every subpermutation, or if you wish, pattern density, is 1 over k factorial, which is its expected density in the truly random permutation, and ask a question, is there again a characterization through finite substructures? Is there, in particular, is there k0 such that if the density of every k0 point permutation is 1 over k0 factorial, is the sequence quasi-random? And we approach this using the theory of permutation limits, which was developed by Hoppen, Kohayakewa, Moreira, Rath, and Sampaio. And essentially, what's happening is that we represent the permutation as a probability measure on a unit square, where the horizontal direction encodes the left to right direction, and the vertical direction encodes the orders, the numbers appearing in the permutation. So for example, if I take the measure with the support on the main diagonal, so this measure will correspond to permutation 1 to n. This measure will correspond to permutation n to 1. This might be, for example, 1, 3, 5, followed by 2, 4, 6. This is a random permutation, that's the uniform measure. And with these measures, again, through the regularity of permutations, which was developed by Cooper, one can link the properties of these measures to the permutations appearing in the sequence and study the questions, combinatorial questions on permutations in the sequence using analytic methods. And this is what we did with Oleg. We actually proved the conjecture of Ron-Graham with the best possible K0, namely K04. And actually what we learned like a couple of years later, that essentially equivalent results were actually known in statistics under very different names. like on the so-called independent test. So the result with K0 being 5 was actually proved by Hevding in 1948, except the language is like very different language from combinatorics. But the result actually is talking about quasi-random permutations and where finite substructure characterization, and this was later improved by Yanagimoto in the 70s. So I have here an example that this K04 is the best possible. So we proved conjecture with K04. But let me skip this example in the interest of time, and maybe let me look at the following question. So with Oleg, what we did is we proved that that in order for the sequence to be quasi-random, one needs to know the density of all 24 4-point permutations, and the question is it enough to take a smaller subset? And actually, in the case of 4-point permutations, it's possible. There's an 8-element subset that I will show on the next slide. But if we happy to take a mixture of lengths, so we happy instead of only 4-point permutations to take maybe some smaller and some larger, when recently Crudel, Dukes, and Noel, they actually showed that there's a set of 6 permutations, 2 of order 3, 4 of order 4, which is quasi-random forcing. And for the lower bound, a student of mine, Martin Kurečka, have shown that one needs at least 4 permutations. So if we're looking for the smallest possible set of permutations that characterizes quasi-randomness when the size of that set is between 4 and 6, fewer than 4 cannot do. We actually have now a very recent result that there is no subset of 4 permutations of order 4 that is quasi-random forcing. There's a general upper bound of 6, but the question is, of course, like whether this 6 can be further brought down. So let me maybe show you this 8-element sets of 4-point permutations. We don't know whether they're minimal if we require the density each of them to be 1/24. But what we do know is that they're minimal if we require their sum to be their number divided by 24. So we actually have a more general result where instead of looking at the density of one permutation, we're looking at the sum of the densities, and we're able to show that the quasi-randomness is actually captured by the sum of the densities of any of these sets or their complements. As you see, they're rather symmetric, which is not coincidental, because we actually show that there is no other quasi-random forcing or some quasi-random forcing subset of 4-point permutations, and this was again based on Analytica. So I don't maybe want to go too much into details. I think since I started late, but I don't want to go too much over time, let me just skip the slide on the Latin squares, and let me go to the summary. And I see Prita is already getting a little bit nervous with me going over time, so I promise I will be very brief. So what I did is that I overviewed the classical results on quasi-random graphs. When I talk about the analytic view, and in particular I talk about step graphons, there is and the interesting open problems here is whether the structure of k-step graphons can be forced by linearly sized graphs. Recall that we improved the bounds on the order of graphs to k-squared, but we don't have a superlinear lower bound on the order. For tournaments, the open question, which seems to be very intriguing, it's not like even clear like what the characterization could be, should be the classification of quasi-random forcing orientations of cycles. And for permutation, similarly challenging question, which there's now quite a large body of literature on, is the quest to find the smallest quasi-random forcing set of permutations. So recall the sizes between 4 and 6. And I didn't talk about Latin squares, so maybe let me skip them here. And thank you for your attention.
Okay, thank you, Dan. Let's give an applause for Dan for his very interesting talk.
Okay. Thanks.
Okay, so Pak Edi, should we go directly to question and answer, or?
We present some song or?
I don't know. Do you still have time, Dan, or?
Yeah. I still have like 10 to 15 minutes.
Okay.
All right.
I planned a
Okay.
little bit like extra time, but so.
All right, that's fine. Okay, so I think I will give the screen to Pak Edi. Pak Edi.
Okay, so we will present some song. This song is the title is The Sound of Silence, and sung by one of the singer is here. This is Rinovia. Okay, let me get here.
Hello, darkness, my old friend. I've come to talk with you again. Because a vision softly creeping left its seeds while I was sleeping. And the vision that was planted in my brain still remains within the sound of silence. In restless dreams I walk alone, narrow streets of cobblestone. In the hell of sleep, I turn my comfort on them. My arms that's lit the dark. That's the sound of silence. And in the naked light I saw a thousand people, maybe people talking without speaking, by hearing without seeing, by writing song. Disturbed us all. My love. And there goes into and the sunset was in the silence.
Okay. I hope you enjoy, Daniel.
Yeah, that was very nice. So I saw a couple of questions actually in the chat. So let me maybe-
Yes, we already have two in the chat. The first one is from Pak Edi. So he
Yeah,
asks,
Yeah, so I think like of course like the good start is the paper by Chung, Graham and Wilson. Like even if the paper is 40 years old, like it and maybe doesn't use the current language of the theory of combinatorial limits, even if some arguments can be basically our combinatorial limits arguments, just like not yet using the language. Like it would be a good paper to start. Of course, like if one wants to learn about the theory of combinatorial limits, the book by Lovas, large graphs and networks, it would be the ideal resource. And maybe more on the extremal side, but of course covering quasi-randomness quite a bit. Like we're currently preparing a short survey with Honza Volec, Andrzej Křešík, and Jean-Sebastian Sereny. But I have been optimistic for the last year that the survey could be finished in a couple of months. So I perhaps would not like promise it to be available soon. But Honza and GS did quite a lot of work recently. So I would be hopeful that we will put it on archive. But this will be maybe more focused on applying the flag algebra method, but definitely like explaining it on simple non-computer assisted examples. But there's no like a survey of recent results on quasi-randomness, and the results are rather spread throughout, which somehow goes to the next question by Favas, and which results are done like combinatorially and which are done by computer-assisted methods. A lot of results which I mentioned are done by computer-assisted methods, and there are actually two different kinds of computer-assisted methods. So one is the flag algebra, which I have mentioned, but and the other one is looking for specific examples. So in particular, when we were looking, we were like, for example, trying to exclude some tournaments to be quasi-random forcing.
Yeah.
I don't know whether I should go back to the slides, so maybe let me do it, but it's clear which results I talk about. Oh, very good. So for example, so maybe I would say there are like roughly like three types of methods. So for example, this result with Robert and Adam, like the computer assistance is different when in the flag algebra setting. The computer assistance is to verify, to find and verify the examples we have were actually examples. When some of the results are proven using the flag algebra method, so it would apply, for example, to this result with Tim, John, Janne, Mariam, and Honza, or it would also apply to this result by Crudel, Jukes, and Noel. And but some results have purely combinatorial nature. In particular, if one goes to this proof that we have with Oleg and about settling the conjecture of Graham, and this is like pure combinatorics. There's no flag algebras, no computer. And so I mentioned kind of four types of different arguments. So I mentioned two which were computer assisted. Now I mentioned like purely combinatorial. And in addition to these purely combinatorial arguments, we have actually a lot of algebraic arguments, like spectral arguments, where we're looking at the spectra. Either we may think of spectra of graphs, tournaments, like just the spectra of the adjacency matrix, or when we go to the continuous setting of the spectra of the associated linear operators, which happen to be compact. So fortunately, the spectrum is quite nice, and we can apply the standard tools from functional analysis to deal with that. And which open problems I would consider to be lighter for students. So I mean, it always depends on the ambition. And so what I do believe is that perhaps the kind of the lightest is to continue the classification of the quasi-random forcing orientations, because I mentioned that the spectral arguments seem to be very successful. And what I actually did is that I mentioned this result with Andrzej, Bartek, and Daniel. We go back to this one. So with František Řešík, Daniel Ilkovič, and Bartek Kilak. And when I actually Daniel Ilkovič is a student of mine, and I asked him whether he can complete the classifications for length 12. He's a very smart student, so I was not surprised that he did it within a week. And it's again, everything is spectral. So it seems that basically what one needs to do, one needs to apply just more careful estimates on the eigenvalues and how they interact with each other. But in some sense, it seems, at least like on the next length case, that the methods are already there. And what we kind of missing is like somebody who like puzzles, just looking at these examples and seeing what puts them on one side and what puts them on the other side. So if I should like pinpoint a problem that I think might be good for a student, then I would say maybe look at this one, because you may see the pattern that we so far don't see. And even if you don't see it, like your work will not get wasted in the sense that most likely there's a good chance that one can complete a characterization of like 14 or 16. So even if like one will not discover the pattern, which hopefully is there, when still like some results could be obtained. So I would say that this might be the most suitable problem for a student.
Okay, is there any other question? Okay, no. So probably if there is no other question, let's thank Dan again for a very inspiring talk today. And I will give back the screen to Pak Edi.
So before that, let me thank you for the invitation. It was really nice to be here, and I'm very grateful for the also inspiring questions. And
Okay.
and I don't want to like, sorry for jumping in the middle when I didn't have the word, but I really wanted to express my thankfulness for being able to join you today.
Okay.
Okay,
So
thank you.
thanks again, Professor Daniel Kráľ, for nice and inspiring talk. And on behalf of Combinatoric Mathematical Research Group, we would like to present you some certificate and also some small token. So let me show you the certificate. Okay, so this is the certificate of this lecture, and this one is thank you notes from us for you. So I will send these two documents by email to you.
Thank you.
Yeah. So hopefully you enjoy, and again thank you so much for your lectures today. Hopefully next time you can come to Bandung. So
yeah, it will be nice. So I will keep it in mind if I travel like in somehow in Southeast Asia or Australia.
Yes, you can combine. Yeah. You mentioned that you have a student in Melbourne, right?
No, I had a student.
You had
Okay.
Okay.
He was too good. He already graduated.
Yeah, already graduated. Okay. Now you can make another student in Indonesia, in Bandung. We have plenty of people here interested in graph theory. Okay, so thank you, Dan, and thank you everybody for coming in this talk today. So we end this meeting. So see you next month. Okay.
Okay, thank you.
Bye
Goodbye.
bye. Terima kasih, Daniel. Ya. Bye. Terima kasih semuanya atas kehadirannya ya. Oke, saya stop recordingnya.